So the first thing we calculated was a call and a put using the Black-Scholes model, and the results can be seen here. And we did this by calculating the intrinsic and time values, which can be seen just here. Next we performed a sensitivity analysis, and this diagram can be seen just here. And this shows the effect of changing the parameter inputs. The first diagram shows the effect of changing the asset price and the volatility on the time value of the call, while the second diagram shows the effect of changing the asset price and the volatility on the time value of the call. The diagrams show that the results are quite similar, where changing these inputs has a positive effect on the time value of the option. We also made calculators for a call and a put, which can be seen here. So any parameter inputs can be put into this and it will calculate the results. Now, the next step was to recalculate the time value of the option using the binomial approach. However, this was extremely computational intensive, so the maximum number of steps that we were able to use was 10,000, and the results are illustrated here for the European options and here for the American options. Now, we then analysed whether our binomial converged to the Black-Scholes model. As you can see, as the number of steps in the binomial was increased, the time value of the option increased. And in the long run, we found that as the number of steps were increased, our binomial converged to the Black-Scholes model. We then ran the binomial in C++, and the results are illustrated just here. And the code used was the Lazen-Reimer binomial tree.
Okay, so the next thing we had to do was calculate the Greeks using both VBA and C++ methods. Illustrated here are the delta call and delta put options, and the graphs indicate that the change in the value of the call with respect to the change in the stock price. It's seen that the rate of change increases at an increasing rate and then reaches a certain point where it begins to increase at a decreasing rate, eventually leveling off. The analysis in a bit more depth is found here, and alongside it is the analysis of the gamma, which we calculated both analytically through the VBA and through a numerical method, which can be highlighted here. Following on from that, we have the vega, the theta, and the rho. These are calculated analytically. The vega first of all. As you can see here, for a call, the analytical vega, which makes reference to the effect of change in delta with respect to the change in stock, it can be seen that the delta has its most influential stage just below the exercise price of 100. To the right, the numerical vega that was calculated shows a slight variation in this. Alongside it is theta, which determines the effect of time decay on the value of an option, as can be seen through the graphs here. There's a small analysis here, just to clarify anything. And finally, alongside it is an analysis of the row, which deals with the rate of change, or the effect of the change in interest rates, which is seen there. Just over here we have a couple of screenshots from C++. If I zoom in a little bit, you can see that the call option was calculated through the Black-Scholes formula at €9.17 and through the VBA function. Also here, through the C++, it works out at 9.17 and 9.17. Likewise with the put, it was calculated using Black-Scholes formula, which is found here and here, and then using the VBA function found here. The screenshot of this is found right here, and again it lines up with the other figures. Moving on to the butterfly strategy, it's made up of 2 long calls and 2 short calls. The long call is found here in the orange line and the blue line, and the short call, which is this formula up here, minus 2 times C2, is made up of the grey line. So we use these parameters over here on the left, with exercise prices varying from 70 to 130, and the middle exercise was 100. Dealing with the analytical vegas and thetas, the analytical numerical vega is compared here, where a change in sigma around C1 and C3 has a positive effect on the butterfly portfolio, and in the middle it has a negative effect. Likewise with the theta, it's actually the opposite effect. Any change in time around the lower or upper exercise price has a negative effect on the value of the portfolio, but a positive effect on the middle exercise. Moving on, the ESO is here, and we calculated it through VBA also from Benninga. The ESO call is here and the Black-Scholes call is there. The graphs are here to highlight any differences, and the ESO vega is also found here. Finally, the delta hedging strategy that was implemented by Hull. There's a quick analysis of it right here regarding the vega, the theta, and the rho also, which are found over here, and the dynamic and static replication, and the argument made by Derman and Taleb.
Next, we downloaded the data for Ford Company on the 25th of November 2015 from Yahoo Finance. I gathered the data for 7 time periods ranging from December 18th up to the 17th of June 2016. Then I truncated the data between call prices of 12 to 16 for the time periods. Next, we made 3 columns with the date I gathered the data on, a column with when the option matured, and the difference in days seen here. Also downloaded the historical volatility daily data from the 18th of December 2014 to the 30th of November 2015, and calculated the percentage change between them and also the log change, and this can be shown on the graph here. Also, for the implied volatility, we used the Black-Scholes function for implied volatility, and we inputted the the stock, the exercise, the rate, the dividend yield, and the time and call market price into this to get our implied volatility. And this is also seen on the graph here with an explanation here. Next was the implied volatility and fit, and this was based off model 3 above, and we needed to calculate k, k squared, t, t squared, and k multiplied by t. And then we also used the Linus function to calculate a5 to a0, which was based off our implied volatility and this recently constructed table. From this we were able to calculate the IV fit following model 3 above, and on this graph here it shows the implied volatility for 23 days and also the IV fit for model 3 for the 23 days also. And from that we could do the IV surface and smile seen in these diagrams here using the data from previously. And then we also constructed a data table here which was used to give the volatility surface and the volatility skew, and a description can be seen here from this button. Next was the butterfly, and we used the same R throughout as we did previously and same Q, which was obtained from Yahoo Finance. And then there was one low long call, one high one, and a short call in between them two stocks. And then that can be seen on the butterfly spread here, and this is where we'd be making the profit in here, and the triangular part. Next was the binomial tree, and we used the exercise price of 14.55, which was on the date we had obtained the data. The volatility here is the one that was closest to the stock price, which is 14.5, so we used the 0.2255 volatility here. And we also did a 6-step binomial tree, and the upswings and downswings are seen here and also in this table here. Following on from that, we were able to construct this table here, and the 14.55, which is the underlying, is correct as it's 0 here, using also this table. And finally the Graham-Charlier model, and this estimates the skewness and the kurtosis. And the underlying figure here is the first one of the stock here, based off the historical data from earlier. We also calculated the returns, the difference between them. And then these are the risk-free, which is used earlier. And we used functions in VBA to calculate the volatility, the skewness, and the kurtosis. And then from that we're able to input the Graham-Charlier call into VBA to give us our call price. And then this can be all explained in here, where we can see that the Graham-Charlier call is higher than the Black-Scholes call, and this is due to the positive skew and also the negative kurtosis.